Hello viewers, welcome you to this MOOC program on engineering mechanics. Today I will discuss on virtual work and potential energy principle. Now in my earlier 2 units I have discussed with virtual work principle and its application. Here another application of virtual work and the potential energy concept can be introduced. Now, what is the learning objectives of this unit? The participants will be able to state various types of conservative forces and will be able to describe principle of potential energy and also know conditions of equilibrium. Now, what are the conservative forces? So, conservative forces are forces for which a potential energy exists. Now, here in this example in the figure 1, here the work done by weights of the bars of the system, that is W1 and W2. Now, when the principle of virtual work of conservation forces to a system can be used, the system must be conservative, which means that the forces and couples that do work when the system undergoes a virtual motion are conservative. Even spring forces are also conservative forces may be considered as. Now, what is potential energy principle? If a system works under the action of conservative forces due to gravity, elastic limits, the use of potential energy concept can be useful. Now, preferably an ideal configuration is under stable or unstable is useful. Now, for gravitational force, in this figure, here you can find that the weight of the body mg and weight of the body in two positions at z1 and at z2 from the x coordinate OY. Now, here F is equal to minus mg. Now, du dz is nothing but mg. So, the potential energy is nothing but mgh, but potential energy is 0 at h is equal to 0. This is a very wonderful concept related to gravitational flow force field. Now, here in this case the spring force, you can find that the force is nothing but minus ky, k is the spring constant. Now, du dy is nothing but ky. So, where u is equal to half k y square. Now, refer to 0 potential energy at equilibrium position y is equal to 0. Now, what is the principle? If a system operates under the action of conservative forces like gravity, elastic elements, the concept of potential energy is always useful, already I have told you. Now, the potential energy U for a conservative force Ps along the direction of S may be given as du ds is equal to minus Ps. Now, the principle of potential energy for the equilibrium of a body or system of bodies follows that the external force P must be 0. Then du ds is equal to 0. So, this is the potential energy principle. Now here in this case, interesting. Now here in this figure 5, there are 3 figures A, B and C. At A, the state of equilibrium is stable. Why? Here the potential energy is minimum. So here del square u by d theta square is greater than 0. So it is very interesting that when the condition is stable, the potential energy is minimum. Now if you go to the figure B, it is an unstable case. Okay, it is a unstable case because it is the state of equilibrium of a homogeneous cylinder. Now here what happens, this homogeneous cylinder in the case number B, that state is unstable, and in that case the potential energy is maximum and the function is del square u by d theta square is less than 0. But if you go to the figure number C, you will find the state is neutral. That is, here potential energy is constant, but the function is d square u by d theta square is equal to 0. So this picture actually will give you the concept of stable, unstable and neutral equilibrium of a homogeneous cylinder or a rigid body. Now the principle of potential energy applied to state of equilibrium of a body or a system with 2 degrees of freedom. Now for independent coordinates x and y, we can write del u del x is equal to del u del y is equal to 0. Now a system with n degrees of freedom needs for it to be in equilibrium. This is the condition. Okay. That means del u del xn is equal to 0. This is the condition for state of equilibrium for n degrees of freedom. Now stability of equilibrium. So steps to analyze the equilibrium condition of 1 degree of freedom system. Now the first step is determination of potential energy specifying the position of the system. Second case, finding of equilibrium positions, that is estimation of first derivative of potential energy. Now third is examination of stability, that is the sign of second derivative of P will indicate the stability of the equilibrium position. Now here in this problem, here you see a one hemispherical element homogeneous is at rest on the plane surface. Okay. So the problem is that prove that it is in equilibrium in the present position and justify its stable position. Now what happens? First, already I have told you how to find out the this step number 1, that is determination of potential energy. Now suppose this hemisphere is rotated angle theta related to its original position. Then quite obviously the potential energy as associated with the weight of the hemispherical element is nothing but u is equal to 3 by 8 r mg cos theta. Now step number 2, finding of equilibrium position, that is estimation of first derivative of potential energy. Now considering the hemisphere is in equilibrium, then we can write du d theta is equal to 3 by 8 r m g sin theta is equal to 0. So it is confirming that theta is equal to 0 is in equilibrium position. Now step number 3, examination of stability. Now in this case the second derivative 3 by 8 r m g cos theta, this expression is positive at theta is equal to 0. That means the equilibrium state is stable. Let us take another example. The example is that the potential energy of a system is given by the expression E is equal to 5x cube plus 10x square minus 3x joules, where x is in meter. Determine the equilibrium positions and states of equilibrium. Now, here in this case, the first of all, step number 1, determination of potential energy. Okay. So, it is already given, no need to determine, it is given in the problem. Now, in the second step, finding of equilibrium position, that is the estimation of first derivative of potential energy. So, for equilibrium position, we are getting du dx, two values, that is x1 is equal to minus 1.469 and x2 is equal to plus 0.1361 meter. Now, step number 3, examination of stability. So, in that case, the second derivative we are getting d square u by dx square is equal to 30x plus 20. Now, at x1 we are getting a value minus 24.07. So, when x1 is minus 1.469, the condition is unstable equilibrium. Now, at x2, when we are applying 0.1361 value, then we are getting d square u dx square is equal to plus 24.03, then that is greater than 0. So, in that case, when x2 is equal to 0.1361, the equilibrium condition is stable. So, my dear participants, I have discussed two examples where you can apply the concept of potential energy. Now, here are the two references. These are the very good books you can follow. This Engineering Mechanics by Professor K.L. Kumar and another book by Engineering Mechanics by R.C. Hebler, Pearson edition, 14th edition, new edition. You can follow this. Thank you very much.